Thank you for the introduction. So, yeah, just to give you a quick overview about my background, because it's kind of important for the things that I want to tell you now. I'm working for a company that is called MGM, so don't mix it up with the movies company, Metro-Goldwyn-Mayer. There's nothing to do with it. We are a software house. And I'm working for MGM Security Partners, which means we provide support for software development teams in-house, but also for external customers. We're doing trainings for developers, penetration testers, deciders, managers, and doing penetration tests, audits, workshops. So the good thing having this broad range of activities is we know the view of penetration testers, so offensive attackers of an application, as well as the defensive and engineering perspective when you implement a new web application and you want to decide how to protect your application against kind of attacks. And these double kind of perspective led me to this talk because the anti-automation approach actually is very interesting to consider from both perspectives. So what is the background technically? I mean, the web web communication consists of HTTP requests and responses. Actually, we all know this. But what does this stateless HTTP protocol imply for the automation options an attacker has, or for the threats that occur from this protocol? If you compare this with a stateful communication protocol, like SSH, for instance, there is no such thing as the automated attack on a protocol level in this case. So with HTTP, however, we have simple plain text messages that are sent to the application, and we can observe the respective response. Meaning, we can send loads, thousands, millions of these requests and see how the application reacts. And there are a couple of attacks and assets an attacker might be after. From a security point of view, or from a protocol point of view, the statelessness of HTTP is very helpful. What we observed in the past years is that the protocol is easily expandable. So just consider the loads of HTTP headers that were introduced, the cookies and all its additional properties that we added. This is that easily doable because the whole protocol is stateless. A stateful protocol would be much harder to extend that way. And also it's more robust. So when I was traveling here yesterday, I came by train from Dublin. And in the train, the internet connection was, well, kind of poor from time to time. And whenever one of my requests when surfing got lost, I just needed to hit F5, reload the page, and I could see the page again. This is not that easy when you have stateful protocols. Again, if you have an established connection and you lose the connection, then you need to re-establish it, and this is usually much harder than just resending this one request. And also the business logic is, well, kind of scalable and movable. I can move the load of the computation towards the client side by using such frameworks like Angular or React, whatever. And this is dynamically decidable, and this is completely different with other protocols. However, the downside is the kind of heritage that we have. HTTP was invented when such stateful applications were not on the line. So we are fighting with control for integrity and also the automated actions that I'm focusing here. So the sequence and the number of requests that reach an application. What kind of functionality of an application might be affected of such requests? So usually the common attack targets are the registration, the login, password request, reset functionality, and the parameterized search queries. There are examples for all of these. I mean, just imagine for a second that it would be possible to automatically register new email accounts. It would be the paradise for all spammers because they just register new email accounts automatically with Google, for instance, send emails, spam emails, as long as the account is locked, and generate a new one. And you can automate all of this. You can go to a party, whatever, and the next day you send out millions and billions of emails. So this must be prohibited. And the same is true for the login as well. I mean, password brute forcing is something that most of us have heard of or know already. So these kinds of functionality is what we need to defend in most applications. Of course, there are applications which have common functionality that must be also protected. For instance, the application of vouchers is something that we use to protect in our applications when we implement. So the detection of such attacks is also non-trivial, and well, assuming that the attacker is aware of some detection technique, it is almost always possible to mitigate detection and to overcome being blocked by respective countermeasures. So, for instance, the most usual way of detecting such attacks is recording the IP addresses and counting the number of requests coming from these addresses. I can, as an attacker, I can scale my attack upwards and see at which point or which number of requests I observe some countermeasures, and I can try and stay just roughly below this amount and see how far I can obtain my my insights, my goals from this attack without being blocked by such algorithms based on the IP address. There's another approach that is based on client-side fingerprinting. You saw on my second slide the burp suite that we also use for our penetration tests and for audits. When I use as an application, when I use kind of client-side fingerprinting in order to detect the client machine and see if the same fingerprint is used for several requests that come to my application, that reach my application, then I can figure out whether it's the same machine that generates these requests. This is also true for the burp. I mean, if I have my browser generating the first request and I replicate this request in the burp proxy, it always uses, of course, the same basic data, meaning the same fingerprint that is always used. So in order to use my burp for these automatic requests, I would need to be able to spoof valid client fingerprints in order to avoid detection by such systems. The problem is I could leave out the fingerprint completely. From an application point of view, those requests might be considered suspicious and face even more countermeasures. We have kind of good experience with so-called device cookies, meaning that honest behavior, so having a valid registration passed or a login and stuff like this, means we set such a cookie in the client's machine, in the browser, and whenever a valid cookie is sent to us, we first of all omit all kind of countermeasures. So this is important for our customers because in the end, I mean, when we propose some kind of detection approach and respective countermeasures, they are always kind of scared that we exclude their honest customers due to false positives. So this is something that our customers require us to avoid at all prices. So this is also one of our the hard walls we never need to reach. So we try to express some kind of trust into this client's device by these cookies, saying, okay, you've been proved to behave honestly, you obtain a device cookie. But of course, every time a request containing such cookies is again or has some malicious input. For instance, we have regular input login attempts with varying user accounts and varying passwords, but each of these has such a device cookie. An attacker might have obtained the first one. We again with identifying such detection approaches and overcoming them and mitigating them. I could, as an attacker, of course, obtain such a cookie and then behave maliciously. So we again need to check whether those trusted requests behave maliciously. And finally, one could, of course, always require an authentication by the user and then relate all this behavior, all the requests to this account and, for instance, lock the account when malicious behavior is detected. So this is an excerpt of detection techniques that we have and that we might use. And whenever detecting an attack, there is a list of countermeasures we might to apply. You all know these captures. One might ask users to add or to enter additional knowledge. For instance, after a couple of failed login attempts, you might also be asked to enter your zip code, for instance, or some other additional information. The target slows down the response time after each attempt. You can send out additional information via text messages or use these proof of work systems, for instance, which we also have good experience with, meaning that the client, the browser, needs to compute some function and generate a response according to the challenge that we pose to the client. And the response gives access to the respective functionality. And this is also very, kind of hard to implement with a burp. I mean, it's possible, but it requires additional work. And IP and user logouts are also kind of known to most of us. So each of those has a number of practical issues, as we needed to learn from our customers. Again, the customer, the honest customer, is the one who must never be annoyed or in order to prevent that they go to the concurrent providers. We also experience problems with denial of service attacks when implementing tar pits because the server load increases significantly. The proof of work systems are actually hard to scale. Who should do the computation? Is it a mobile device? Is it a cloud? This makes a big difference. And also the logout of users is the worst thing that might happen to an honest user. It must be avoided at all costs. Okay, having this in mind, we came up with a kind of help that we use in order to do our consulting for our customers. This is an excerpt of our table of knowledge, actually. Because for these kind of standard functionality that most of our applications implement, we derived from the lessons learned that we have kind of appropriate detection techniques and respective anti-automation approaches. You see, unfortunately, well, more or less unfortunately, the captures are usable in most of these scenarios. However, again, they are not well accepted with most of the customers because they might be annoying, and you know the ongoing arms race between those people overcoming and automatically solving these captures, and on the other hand, those providers like Google with a recapture that try to still protect the functionality from automation. So this is a kind of table that helps us deciding what might be helpful and appropriate here. However, in the end, it's always the customer who decides what is possible to do and what is not. At least, I must say, we had kind of good experience with this table and the lessons that we learned from here. On the penetration testing side, when we test applications that were not implemented or consulted by us, we regularly observe that there are some holes in the protection of the customer's applications. So this is a number of countermeasures that proved well. Okay, coming to the conclusion just in time. There are still open issues that we are facing. So how do we protect machine-to-machine APIs? This reduces the number of countermeasures to just a couple because the user is not available anymore as a resource to solve some kind of challenges. And the other thing that is equally important, how do we distinguish attackers from the Google robot? Our customers, for instance, implementing online shops, they want Google to list and to crawl their offers and show them whenever customers are searching for. However, they want to prohibit that concurrent shops scan and monitor their prices or even put too much load on their shops and their servers. So this is a very hard problem. And Google itself, by its requirements, makes it even harder because they want to prohibit that people distinguish between Google and other crawlers. And this makes life even harder. And the user acceptance is still the biggest problem because our customers don't accept any kind of approach and solution that might have an impact on honest users. From a penetration testing point of view, we know that whenever we report problems with anti-automation, missing anti-automation, this is kind of the most expensive and hardest problem to implement afterwards. And on the other hand, when we are involved in the implementation process and development process from the beginning on, we can propose appropriate approaches then, and the costs are negligible compared to leaving out the security experience in the beginning. So it costs almost nothing in the beginning, but it's very expensive doing it in the aftermath. So this is one of the biggest impacts. So, thank you.
Do you want to take questions or anything? Bastian? Do you want to take some questions? If there's any questions for Bastian?
Just one question. You said that CAPTCHA isn't suitable for login.
Yeah.
Can I just ask what your reason is? Because
so technically it is actually. We are very convinced that we want to avoid the use of captchas, and our customers confirm this. We want to avoid the use of captchas whenever, or for functions that are used regularly. Meaning if you log in every day to some application, you don't want to solve a captcha every day. You usually do the registration with the application just once. And we also hope that you don't forget your password every day. So for these kind of rare functions, you can require the customers to solve the captcha, but for the login, none of our customers accepted a captcha because they said people don't come back to us and they go somewhere else and don't use our
user experience.
Yeah, because of the user experience. So this is why I said technically it is applicable, but I mean the title was practical experience and practical approaches, and this is why from this point of view captcha is not a feasible solution for the login actually.
Awesome.
Yeah.
Do you have an example for proof of work?
Yeah. We decided for an approach that we use that is similar to the hash cache approach. It's based on computing hash collisions. That is also the basic for the Bitcoin system. What we in fact do is our application takes some random string, computes the hash of it via SHA-1 or SHA-256, and provides to the client the prefix of the input to this hash function and leaves out the last couple of bits, and you can set the level of the computation level that is required to solve the captcha via the number of bits that you leave. And you say, okay, this is the prefix of the solution, and you provide the actual hash. And the client, usually in JavaScript or via mobile app, needs to compute the missing bits. So what bits do I need to append to this input in order to finally obtain the hash that I know? This is the challenge is the prefix of the input plus the resulting hash, and the response is the missing bits of the input.
So you're actually checking that the client knows JavaScript. That's the check.
Depends. So when we have the web API, we require that the browser is allowed to execute JavaScript. If we have a mobile API, for instance, we code this the solution to this challenge in our mobile code. So also with JavaScript, of course, we code the solution ourselves. So the customer or the client, in this case the browser, knows nothing about it. They just execute our code.
So how to detect an automation, for example, Google Chrome now will have a headless mode.
Yeah.
Right? So how you will identify that this Chrome browser running in headless mode, not from legitimate user, from someone who's trying to make an automation platform for some data harvesting.
Yeah. So from our criteria, we might apply the IP address the client is running from. If you have kind of a crowd running it, we might still use the fingerprints. They are probably the same or similar to all of these instances that are trying and running this attack. These are, for this kind of attack, probably the most helpful detection techniques. But in the end, I must also say there is no 100% detection as there is no 100% protection. So an attacker spending enough efforts might mitigate all detections and overcome all protections. This is what I'm very convinced of. I have no formal proof for this, but knowing all internal working of the application, for instance, having this knowledge, I think it is really possible to overcome all of this kind of protection. But, I mean, the burden is fairly high, so we want to protect against external attackers usually.
So from your experience, customers more unhappy having a false positives or false negatives?
So our customers usually more accept the false negatives, meaning accepting a successful attack, then locking out honest users, but this always depends on the impact of this attack. So if the impact is someone manages to generate 100 additional accounts, they usually accept this. If the impact is your application is down for 2 days and your private data of your customers is lost and gets public, whatever, then they will probably decide differently. And this is also one of the biggest problems for us as consultants, to explain our customers why they need to do it, what might be the impact. These attacks really exist. You need to defend, and this is always a hard process. But after going live, all of our customers confirmed that, oh, now we see we are under attack here, and there's so much traffic here coming in, and we can't manage to monitor it all and to classify and stuff. And good that we took protection in advance. So usually, in the end, we get confirmation, but during the development of the process of the application, we have a very hard time to convince them applying some protection. In the end, they are happy. This is the biggest thing.
Awesome. Thank you.
Okay.
All done. Thank you again.
Thank you.